Hello everyone, welcome to second lecture of digital image processing of remote sensing data course, and in this particular topic we are going to discuss different techniques of image acquisition, that is means digital image acquisition, and mainly we will be now start focusing on satellite images, and that's the because we now know what are the digital images, and it's a snapshot taken by a digital camera, handheld mobile generates digital image that can be stored in a computer, displayed on a screen and printed. Now acquisition by the satellite. So there are various types of sensors exist or have been used earlier. And so here the major difference is, which starts from these sensors, there are two types. One is passive sensors and another one is active. Let me explain what is passive sensors. Passive sensors are those for which you don't require any energy. Natural energy is more than sufficient to acquire the images. Like sunlight or solar energy is the mostly available energy, and the sensors which are working in visible or infrared or thermal infrared part, and they are all passive sensors. So sensors which are on board of satellite, the most common one are the passive sensors. Whereas for active sensors, the sensor itself has to provide the energy to scan a part of the earth. And this is possible in microwave region of the EM spectrum. So there are sensors on board of different satellites. Earlier we had a satellite like ERS. So we had a SAR sensor. Now the latest in that series is a Sentinel, and we are having again sensors in active category. So passives are more common. If we go for passive sensors, then there are two types. One is non-scanning sensors, another one is scanning sensor. And ultimately we end up with non-imaging and imaging sensors in case of non-scanning sensors. Now passive microwave remote sensing is also possible. That means that the natural micro or natural emission which is in part of microwave region can also be detected by satellite, and there we call passive microwave, but which is not very common. So that is why microwave radiometers in non-imaging is given there, but the most common is are the passive scanning images. Scanning images are the most common, and they are there. Optomechanical sensors were also very common, but they had some problems. So those are not now very popular. Whereas your digital cameras or photo cameras, they are all non-scanning because you don't have the scanner. They are imaging, and we find these non-scanning imaging sensors in your cameras. So we can cover a monochrome, that means black and white images, natural color, infrared, color infrared, and other possibilities are also there with such cameras. But which are non-scanning, that means they are taking a snapshot. Let me give you an example. You must have seen the flatbed desktop scanner where we put a sheet of paper or some drawings and then we scan it. So line by line is being scanned. So that is what we say is scanning. Whereas when you take a picture from a camera, it's a snapshot, and that we put in non-scanning. So this is the major difference. Like there is a satellite, though it is a communication satellite, but it acquires images through a sensor, but it's a snapshot. And the example of that satellite is like latest in the series is INSAT 3D. So INSAT 3D will provide the data maybe every half an hour in a snapshot of India and surrounding countries. This is mainly used for weather forecasting and other things, but it's a non-scanning. So that one has to remember. Whereas scanning cameras or scanning sensor will record line by line. NOAA, HRR, Landsat, MSS, all these sensors are scanning sensors. So there can be even microwave sensors and other sensors are possible there. So there are variety of sensors are available on board of different satellites. It depends what quality of images, what resolution of images we are looking for. Active, as I have mentioned, that in case of active remote sensing, the energy has to be sent by the sensor itself, and then backscattered energy is recorded by that same sensor at little different time, at different location, and that is the time versus pulse, that the pulse is sent. So that is also shown here, that the return pulse may be different for different. So like here the object is house, which will give you the return pulse much higher than the vegetation, and whereas a flat ground may give you a little uneven but very low pulse. So that kind of reflection is there. If there is a metallic objects, they will give you much more backscattering. Whereas in case of passive sensor, the main source of energy is there, the sun, as also shown here. And what we record in thermal infrared brightness, temperature, or just reflectivity which is coming through your atmosphere to the sensor, and that is recorded. So there is passive sensors can record surface emission, and that is in thermal, cosmic backgrounds, rain emission, all those things can be recorded by passive sensors. This is what is a part of EM spectrum is shown. On the top, that means in the red colors, all are active sensors, which I will take little later, whereas passive sensors are given here in the blue. So let's start one by one. Ultraviolet imagers. It is not possible through satellite imaging to capture images in ultraviolet part of EM spectrum, and the reason you can think is because of presence of atmosphere. The atmosphere between your sensor and Earth's surface doesn't allow the light, the ultraviolet light, to pass through, and therefore that doesn't reaches to your sensor, and therefore though you may having a sensor on board of a satellite, but the ultraviolet light is not reaching, therefore you don't record anything. The most common one is the visible and near infrared. So here a lot of satellites are having, in the first lecture as I have told you, different sensors, Landsat series of sensor, Landsat MSS, TM, ETM plus or OLI series. They are having many bands in this part of EM spectrum, which is the visible or near infrared. So this is the typical wavelength range between 400 to 1100 nanometers, or 0.4 micrometer to 1.1 micrometer. The another part of EM spectrum where atmospheric windows are open, it means available. That means the atmosphere will not block the entire energy to reach to the sensor, and that another window is available in thermal part, and the bandwidth is quite high here, 8 to 14 micrometer, as mentioned in the previous lecture, that more because this thermal energy which is coming out of the different objects is not sufficient to reach to the sensor, and therefore you need a broader band sensors to record the variations, so that distinction between different objects is recorded by the sensors, and therefore you are having broader, means the spectral resolution is relatively poor here as compared to visible bands of different satellites. Then the passive microwave region, which is giving here in the blue color, starts from roughly 0.5 centimeter to up to maybe 100 or maybe 20 or 100 centimeters. Now if we go for active sensors, then the laser fluorescence sensors are possible, but there are no satellites, regular satellites, which are covering this part. So we will focus more on this. In the previous lecture I have given some example. The sensors which are in the C-band, the latest like Sentinel, which is having a SAR, that is synthetic aperture radar type sensors, and it is covering the part of EM spectrum, and which has given a C-band. So the band, the part of EM spectrum which is covering is this region. KU band, K band, other parts are X band is also in, like in RadarSat, which is a Canadian, used to be a Canadian remote sensing satellite, used to cover in X band, a little off or little earlier in EM spectrum than your C band. So C band is the most common in microwave satellites, and that is active satellites. Now passive sensors, as I have already mentioned, that you require sun's energy, which is available plenty in various parts of the earth, and which is or absorbed or re-emitted through thermal infrared wave bands. And remote sensing systems which measure energy that is naturally available are called passive sensors, and which is the most common. Most common remote sensing is passive remote sensing. Passive sensors can only be used to detect energy when naturally occurring energy is available. That means mainly in the daytime. In night time the sun is not there, but still the energy which here, the naturally energy which is available, which is getting emitted by different objects because they are above absolute zero, so that our passive sensors in thermal part of infrared region of wavebands can record that energy. So like NOAA or Landsat can also record images even in night time, but not of visible part, but only in the near infrared part or mainly in the thermal infrared part. But still they are all called passive sensor. For all reflected energy, that means when you are having the sun, this can only take place during the time when sun is illuminating the earth, and in daytime it is all possible. So various satellites orbits have been designed like this, so that you cover a large part of the earth in daytime, and accordingly you can record the data. So the night time with thermal sensors, and there is no reflected energy available from the sun at night, and though your thermal sensors or near infrared sensors might work, or infrared sensors might work, but mainly thermal infrared are useful. An energy that is naturally emitted, such as thermal infrared, can be detected day or night as long as the amount of energy is large enough to be recorded. That is why the bandwidth of thermal sensors is much larger. Now in active sensors provides their own energy source of illumination. As I have already mentioned, the sensor itself has to send energy in form of pulses, and when it moves it collects later on. That is we call as backscatter. So the sensor emits radiation which is directed towards the target to be investigated, and the radiation reflected from that target detected and measured by the sensor. There might be some attenuation, some changes in that energy, but nonetheless it can be recorded by the same sensor at different position. So advantages of active sensor include the ability to obtain measurements anytime. That's the biggest advantage, regardless of time of the day or season. That means it can go through the clouds, because the particles which are there are much smaller than the microwave bands or the lambda wavelength, and therefore it can work day and night, because you don't require a natural energy for microwave sensors or active sensor. The active sensor by themselves, they transmit or emits the energy towards the earth, and backscattered is recorded. So that is why it is said that anytime it is possible, regardless of time of the day, because your sunlight is not required, or season, whether cloud free or not. Other advantage with the active sensors, if you are having dry soil, then they can penetrate up to few meters. But as soon as they get the moisture or water, then the penetration stops. And in India, there is one of the best examples, the lost courses of Saraswati river in parts of Rajasthan and Haryana were discovered based on active remote sensing satellites, that is using microwave images. So active sensor can be used to examining wavelengths that are not sufficiently provided by the sun, such as microwaves, or better control the way a target is illuminated. However, active sensors require the generation of fairly large amount of energy to adequately illuminate the target. That means if the satellite is acquiring the data, it requires huge amount of energy, because the energy has to be sent to the surface of the earth, and then backscattered has to be recorded. So the larger zonal panels, that means larger payloads, more cost, and so on and so forth. So these are some disadvantages also associated with microwave or active sensor. The best example of active sensor is synthetic aperture radar. I have given the example like in Sentinel, Band C, and it has having the SAR. So SAR is the most common technique. One of the examples from our own Indian remote sensing satellite, which is RISAT-1, which was launched on 22nd September 2012. It is showing a part of Tripura. These are the different hill ranges which you can see, water bodies and so. And because as you know that this part of the country is most of the time is having cloud covers. But as mentioned that in case of microwave or microwave images or active remote sensing satellites, these clouds will not create any problem, and therefore completely cloud free images can be acquired. And the advantage of this in case of flooding, whenever there is a flooding, northeast flooding, especially in Brahmaputra is very common, but at the same time you are having cloud cover. So our other passive remote sensing images becomes useless because of cloud cover or less useful. So therefore, if we are having microwave satellites, then we can acquire cloud free images. We can distinguish the areas which have got inundated due to flooding in a particular river. So that is a very big advantage. Also geological structures and topographic details can also be acquired very nicely with microwave satellites and sensors than your passive satellite sensors. So that is another advantage. Now there are the most common one in passive remote sensing is the multispectral scanning. That means that within a sensor you are having different bands covering different parts of EM spectrum, might be having different bandwidths for different bands, and they are all in a one sensor on board of a single satellite. So that is why we call a multispectral scanner. So in satellite remote sensors acquire data using scanning systems and not a snapshot like in case of IRS 3D. So these are all scanning, not non-scanning, which imply a sensor with a narrow field of view, that is IFOV is very narrow, and very narrow means it covers a very small part of the earth, that means higher spatial resolution that sweeps over the terrain to produce an image. And the image are recorded line by line, pixel by pixel. And there are two main modes of scanning to acquire multispectral images. A cross track, that means when the satellite is in the direction the satellite is going, then a cross track, or maybe a long track scanning, that is push broom scanning. And the examples are also shown. The whisk broom scanning was in case of Landsat, where a spot and iconos represents the along track scanning. But these are the optomechanical devices, some of them, and they create their own problems. So those are little different issues. And like for example here, given from the latest series in the Landsat 8, also called OLI series, and different bands are shown here. The images which have been acquired against different bands is also shown here. And what we see that they are giving different appearances. We can take 3 images out of these, assign 3 colors, primary colors, blue, green and red, and then a false color composite can be created because it provides a better interpretability. This concept of false color composite has already been discussed in previous lecture. Just for completeness, I have brought this slide again here. Now a cross track scanning in which in the direction, this is the direction of satellite movement. And this is the most common one, and it is taking the images pixel by pixel or line by line. So the using a rotating or oscillating mirror, which is here, mirrors, such systems can scan terrain along scan lines that are right angles to the flight line. So this is the right angle, this is the direction of flight, a large arrow is shown here. This allows the scanner to repeatedly measure the energy from one side of the platform to another, and keep moving like this, and keep recording the data, and data are collected within an arc below the system, typically of some 90 degree or maybe 120 degree. Lesser the arc, more the distortions will be there. Higher the degree of arc, more the distortions, but the swath will increase. So there are always a trade-off in that sense. And this solid angle is called IFOV, which is measured in radians, whereas your pixel is always we discuss or we measure in meters, which is the decide your ground resolution. And this is the scan direction, because this device or the scanner oscillating mirror is scanning in this case from left to right. So that decides the direction of your. The incoming energy is separated into several spectral components that are sense independent, and this is all done within the sensor. And the third one is the non-thermal wavelengths component is directed from the grafting through a prism. These are the arrangements within the sensor or diffraction grating that splits the energy into continuum of ultraviolet, visible, near infrared wavelengths. At the same time, the dichroic grating disperses the thermal components of the ongoing signal into its constituent wavelength. So it separates out and sent to different bands. This is the scanning system. Detector and referencing systems are there. There are different types of scanning systems are there. An optical mechanical scanner is a multispectral radiometer by which images can be recorded using a combination of motion of platforms or a rotating or oscillating mirrors. Optical mechanical sensors scanners are composed of optical system, a spectrographic system, a scanning system, detector system, and reference system. So all are there. Again, here you are having a flight direction, and it scan line direction is there, and it records the data. So multispectral scanners on board of MS Landsat and TM, NOAA AVHR, all are examples of optical mechanical scanners. Along track scanners, as the cross track system, along track or push broom scanners record multispectral images data along a swath beneath an aircraft. So instead of in a different direction, it is just below that it records, and you are having a array here which records the data. So also similar is use of forward motion of satellite to build up an image by recording. So instead of moving anything, it exploited the movement of the satellite and keep recording. So you have reduced one more optomechanical arrangement. So optical arrangement might be there, but mechanical arrangement is not there, and therefore such sensors are also very popular. However, there is a distinct difference between along track and across track systems in manner which each scan line is recorded. In along track system, there is no scanning mirror. Instead, a linear array of detectors is used. As I have already mentioned, this A is linear array of detectors, and they are direction parallel to the flight line direction, and linear arrays normally consist of numerous CCDs, position end to end, and they record one by one. So line by line is recorded by this, and this is how the scanning is done. So this is another very efficient way of scanning. Each detector element is dedicated to sensing the energy is a single ground. So for each pixel in a line, there is a separate CCD. Now these have also created some problems. That means that each CCD before launch of the sensor has to be calibrated identically. Because if CCD itself are giving different energy for the same objects or different pixel values ultimately, then we don't know how accurate these are. So that is why these constraints are always there. So there are advantages of along track scanners. Linear arrays provide the opportunity for each detector to have a longer dwell time or residence time over which to measure the energy from each ground cell. So along track scanners, with that you are having this advantage. The stay time, the data acquisition time is much larger, and enables much stronger signals to be recorded and a greater range in the levels of signals that can. That means ultimately the image quality is going to be much better in case of a long track scanners, and leads to better, as I mentioned, spatial and radiometric resolution, ultimately good quality images, better interpretation, better inferences, more use of the satellite. And the example for this particular here is the push broom scanner in case of our own Indian satellite list 2 and list 3. These sensors where linear array push broom scanner as is through a schematic it has been shown. Now advantages with along track scanners, the geometry along each scan line is similar to that of characterizing an aerial mapping camera. Because of CTs are solid state microelectronics devices, they are generally similar in size and weight and require less power for their operation. And one disadvantage is to push broom system is need to calibrate. This I have already mentioned, that the calibration has to be of highest quality, so that each CCD respond to the same quality of signals in identical manner. As you know that our sky or space is full of satellites. There are now many countries. Earlier there used to be few countries, but now more than 20 countries are having their own satellites. And not one type of satellite, various types of satellite in various types of orbits. The most and the one which is the closest to the Earth is a geostationary satellite. Sun synchronous satellites. And the example from India is like IRS series, Cartosat, OceanSat. These are all polar orbiting or sun synchronous satellite. Landsat is one of the example of polar orbiting or near polar orbiting satellite, Spot and so on. These are the satellites which we use for remote sensing data acquisition. Most common one are these one, from where we are taking that. NOAA HRR is also example of polar orbiting satellite. These are the closest, and therefore you are having very high resolution. The next orbit, which is around 3600 kilometer away from the surface of the Earth. It is giving here this yellow color orbit is giving about 3600 kilometer away from the surface of the Earth, which focuses on a certain part, and this is called geostationary because as Earth moves, the satellite moves. So in relative motion, both are looking the same. The satellite is looking the same area all the time. So we call they are stationary with the Earth, but everyone is moving. So in relative sense, it is stationary. And there are various satellites. So I can call as different envelopes at different distance or in different depth of space. So one envelope is around 840 plus minus 10 kilometer, which is having sun synchronous or polar orbiting satellites of various countries, and from each countries you are having several satellites. So this is all is cluttered with satellites at that distance or that depth in space, around 840-50 kilometer. Then another envelope is around this geostationary orbit, that means 3600 kilometer, and each country might be having several satellites there. Some examples are like Meteosat is given here around this yellow, and then you are having INSAT series. FY, which was the Chinese one, was also very common. GOES is very common. The Chinese FY 1, 2, 3, they were also there, but FY 1, 3, they were polar orbiting satellite, not geostationary satellite. Now in the NOAA series, earlier we had the NOAA series of satellite. Now they are new series in that is called NPOS. So NPOS is also coming. That is a sun synchronous satellite. And this NVSat or Sentinel, they are also in this series of polar orbiting satellites. ALOS, Aqua, Terra Aqua, various satellites. So the entire space at different depths is cluttered with satellites. Some are working, some are dead. And there is another third highly populated envelope in space which is very far, but still it is having many satellites which are navigation satellites, and that envelope is having about 20,200 kilometer deep in space. The best example from GPS series means Navistar series of US. Chinese are also having Baidu. India is also having our own regional navigation system, but it is not fully that our satellites for navigation all are at 20,200 kilometer. Some of geostationary satellites are also being used for navigation purposes. So it's a combination of different satellites, not like American GPS or Navistar system. Russians are also having, and Europeans are also having their own navigation systems. So there are various satellites. This I have already mentioned that geostationary or geosynchronous orbits are there, and then you are this is for the common for the GPS, very far geostationary, they shown as the white color, which is though it is schematic, so the distance is not much incorporated here. So the geostationary at 3600 kilometer, whereas geosynchronous, that means the navigation satellites, one example from Navistar, that is GPS is shown, they are at 20,200 kilometer in deep in space. Whereas in polar orbiting satellites, and two orbits are shown, one geostationary, which we have already discussed, polar orbiting satellites, and near polar, basically they are having about 9-degree angle and keep orbiting in their own orbit. Below or in between, in the center, the earth moves or earth rotates, and therefore the scanning is done. So there are different motions are shown here for different, like this is a near polar orbiting satellite, and these are the geostationary satellites. Geostationary satellites mainly used for communication, telecommunication, for television transmissions. Nowadays they are also being used to take a picture or a snapshot or an image in different parts of EM spectrum for meteorological purposes and forecasting and other things, and also now these are being used for navigation purposes also. So like for our own GPS equivalent regional system is NAVIC, which is using some of these geostationary orbits. The last in this data acquisition, once the sensor has acquired the data, it can record on board, which might be having recording system, and the same time it also transmit the data towards the earth. It has to be recorded. So for that you need to have a setup. Luckily since 2002 we are running a NOAA HRPT satellite earth station. External, this is the rotating antenna is here, and the acquisition system here, this is receiver, and it is controlled by a simple PC and a software. And this earth station is operational since 24th October 2002. It covers, because of relatively lower spatial resolution, it covers a very large area, as you can see, roughly a 3,000 kilometer radius. And that means that if a satellite is coming from north and going like this, need not to be overhead of Roorkee, but still we can acquire the data. But when it is overpassing Roorkee, then the satellite will be longer in contact with the earth station, and we can acquire a longer strip from here when there is a overpass. But when we are having side orbits, then the acquisition time is less, but still it covers a very large area. But because of relatively coarser spatial resolution, and the temporal resolution is high, so in 2 times in a day and 2 times in night it comes in the contact of earth station or vice versa, and then we can acquire the data. And this is the advantage of having wide swath of about 2800 kilometer thick, and entire Himalaya has been acquired just by within a one scene, which is with high spatial resolution sensors, it is not possible. This is how in a normal time, in daytime, visible channels will acquire the data. This is how the same area is covered in night time using thermal sensors. Thermal images might appear as kind of X-ray as we are more familiar with. So this brings to the end of second lecture, that how the data is acquired, and processing part we will see in later lectures. Thank you very much.